So for this next set of examples, they are going to be a little bit more abstract, and so I really need you to, I guess, pay real close attention. Okay, so what we're being asked to do, pay attention real close what we're being asked to do. We're being asked to find the derivative of an integral. Maybe we'll even label that. This is the derivative of an integral. Now, we just proved in this lesson that an integral of a function, that is basically the antiderivative of the function. So taking the derivative of an integral is like the same thing as taking the derivative of the antiderivative. So the derivative of the antiderivative, they're basically going to cancel out, and you're going to end up with just the function. Okay, so you're probably wondering like what the x has to do with it, what the negative pi has to do with it. Well, think back to the way we defined the antiderivative. It's defined as the integral from a, which is some constant, to x of some function. And we never specified what a is because a could be anything. A could be any constant. So the negative pi is just like our a. And so it really has no bearing at all on what the answer is going to be. It's just a constant. Okay, and we have x there, which is our variable for f. And then here's the function inside. Okay, so this integral is equal to the antiderivative of f, but I'm taking the derivative of the antiderivative. So in fact, maybe I'll go ahead and just call this cosine t dt. Just to kind of really bring it home. And what I'm trying to do is I'm trying to find the derivative of this. I'm trying to find d dx of f of x, capital F of x, which is d dx of this integral. So if capital F is the antiderivative of cosine, then the derivative of it would just be cosine. These basically cancel out, and it's basically just equal to cosine of x is the answer. Okay, so once again, the integral is referring to the antiderivative of cosine, which is capital F. But I'm taking the derivative of the antiderivative. So I find the antiderivative, but then I take the derivative of that. Well, I get back to the derivative again, but evaluated at x. This is f evaluated at x, so now the t kind of just goes away, and you're left with cosine x. That's your final answer. The pi, the negative pi, never had any bearing whatsoever, because that was just a, and a could just be any constant. It doesn't matter. It has no bearing on the final answer. Basically, the bottom line is the derivative and the integral sign cancel out, and we're just left with cosine evaluated at x, because the t is just like a dummy variable. And we put the x in because we're finding d dx. Okay, so we have cosine x as our final answer. All right, for number 3, same idea, but we're going to extend it a little bit. So right here, my constant is 0. Doesn't have any bearing whatsoever because that constant could be any number a. So I don't really worry about it. But here, I need to pay attention because it's 2x. It's not just x. So we need to remember that this function here, from a to x cosine t dt, is a function of x. What I have here is a function of 2x. So that means I'm going to have to use chain rule. Okay, because what's happening is my y is equal to the integral from 0 to 2x of cosine t dt. So to find dy dx is going to be like finding d dx of f of 2x. Because it's not from 0 to x right here, it's from 0 to 2x. So I have to find the derivative of the antiderivative and then multiply it by the derivative of the inside. Okay, well, we already have decided that the derivative of the antiderivative is just this function. So like I'm taking the derivative, I'm taking dy dx. So dy dx is the derivative of this. So they cancel out. Okay, so I'm going to have, so this is going to equal cosine of 2x, because it's, you take the derivative of the blop. So 2x is like a blop right here. Just like before when we used to do chain rule. So it's the derivative of the blop, which is just this function of 2x, and then times derivative of 2x, which is 2. So the final answer for example 3 is 2 cosine 2x. Okay, so let me recap on that one. So we're given that y is a function of area from 0 to 2x cosine t dt. So it's not 0 to x anymore, which means it's no longer just a function of x, it's a function of 2x, which means we're going to have to use chain rule. If it were a function of x, it would look like this. So it's like this function, but with a 2x in place of x. And I'm taking the derivative of this function, so I'm taking the derivative of this function of 2x. So the derivative of the antiderivative is just the cosine, but it's the cosine of 2x, and then times the derivative of 2x, which is 2. And so that's our final answer, 2 cosine 2x. Okay, so that one, that's not easy. That's tricky. 4 takes it even another step further. Okay, so in 4 we're told that y is the function of is a function of the area under this curve from sine of x to cosine of x. So now I don't even have a constant here anymore. So now even the lower limit is a function of x. So this is going to be a double chain rule, and the upper limit is also a function of x. Okay, so the lower limit is a function of x, the upper limit is a function of x. So we're actually going to use part 2 combined with part 1 of the fundamental theorem of calculus. And basically what we're going to do is say, all right, the integral of t squared means the antiderivative of t squared. But I'm finding the derivative of the integral. So the derivative and the integral cancel out, and I'm left with t squared. But I have to evaluate that t squared at this limit, and then I have to subtract them. That's what part 2 says. So basically what I'm going to have to do is take the derivative of f evaluated at cosine x minus f evaluated at sine x. I'm taking the derivative of this. Okay, so the difference rule says, all right, I can take the derivative of these separately. Well, this is the antiderivative, so I'm taking the derivative of the antiderivative. So in a sense, they cancel each other out. And I'm left with just cosine x. Oh, cosine squared x. I'm left with this function evaluated at cosine, this one here. So I end up with cosine squared x times the derivative of the blop, the derivative of the inside, which is negative sine of x, minus, so the derivative and the antiderivative cancel each other out, and you're left with the function that was inside the integral, evaluated at sine. So I get sine squared x, and then I multiply that by cosine x. And so after some simplifying and whatever, I get negative cosine squared x sine x minus sine squared x cosine x, and that would be the final answer. So that would probably seem really complicated. Let me simplify it. Basically all I do is the derivative and the integral, they cancel out. So they just undo each other. So you're left with the function that was on the inside, which was t squared. But I have to evaluate that at the upper limit and evaluate that at the lower limit. So that's what this was. This was t squared evaluated for cosine. So it became cosine squared. But I am doing a derivative. And it is a derivative of something of cosine x. So I also have to do the derivative of cosine x, which is negative sine x. And I multiply it. That's chain rule. So it's t squared evaluated at cosine times the derivative of cosine. So that's cosine squared x times negative sine x. And then minus, because that's the rule for antiderivatives, f of b minus f of a, minus the t squared evaluated at the lower limit. So I got sine squared x, and then times the derivative of the lower limit, which was cosine x. And that was the final answer. So those 3 examples, 2, 3, and 4, are probably the most difficult of this whole chapter because they do use that that idea that this integral is a function of x. And then if the integral is a function of something other than x, you have to use chain rule when doing the derivative of an integral. There's a lot of ideas going on here. And these are very famous AP test questions because they really test to see if you really understand what's going on. So you'll probably need to take some time, even read in your textbook. They also describe these same things. Come and see me for a tutorial, and I will do my very best to make it as clear as I can. Okay, but now we're moving on to number 5. Another very, in fact, it's a very sort of abstract idea. So basically we're going to write a function, and we can use the integral sign. We can use the integral sign in our function, okay? That has this as a derivative. So this is the derivative of the function we're going to write an equation for, and then this is a point of the function. So this is the derivative of the function, and this is a value of a function, a value of f. So I could say that f of -1 is 4. Well, this is the notation we've been using thus far. The integral from a to x of, and I'll go ahead and use the function secant of t dt. Because remember, f is the antiderivative of secant, so we can show that by putting integral. Integral and antiderivative mean the same thing. But then the question is, all right, well, what do I do with this point on f? Well, if you think back, I'll do a little think bubble again. If you think back to one of our properties of integrals, if I integrate something from a to a, that equals 0. I can use that fact to help me with this whole like -1, 4 thing. Because if I did an integral from -1 to -1, I would have 0. So if I came back over here to the a and put -1, and I evaluated this for -1, f of -1, I would have 0. So if I added 4 to the outside of the integral, so it's like this would be separate, I would have, and I plug -1 in here and there, I would have 0 plus 4 equals 4. And so this right here, believe it or not, is our answer. Because I can write antiderivatives as functions of areas under curves. So I can use this integral as the symbol for antiderivative from any constant I want to x of the derivative dt. And then the reason I added 4 is because I wanted this function to equal 4 when I plug in -1 for x. And if I plug -1 in for x, I'd have a 0 integral plus 4, and I'd have a value of 4. So these 4 examples, 2, 3, 4, and 5, are all using part 1 of the fundamental theorem, which is the analytical, the conceptual side. When we're solving problems and trying to, find areas and things like that, we're going to use part 2 much more often. Okay, then this last part of this page is on finding area, total area. So as you recall, area under the x-axis is considered negative. And so if you just find like a regular integral, it's going to cancel out positive and negative areas. But if you're trying to find like an actual total amount of area, like if you don't want to do the negative part, you can do that by using absolute values. And this is on page 284 in your book. So basically what you could do is you could find the areas above the x-axis and below the x-axis separately. So you could find those separately. And so you would need to basically find the x-intercepts of the function to be able to split that up. So you find the x-intercepts of the function, and so you can find out what areas are above, what areas are below. You find those separately. And then you just basically make all the negative area positive. You can do that by either multiplying it by -1 or absolute valuing it, and then add everything together. So as a summary, total area is like the absolute value of all the area. It's not taking into account any negative. Whereas the net area is what you would get if you just evaluated the definite integral. And that's where positive and negative areas cancel each other out. Okay, so we're going to use this idea in the next video.